Okay, you guys ready to get started? Yeah, 4 o'clock. All right, just a reminder, I am Dr. Volstead. I haven't led class yet, so it's nice to see all your shining faces. I cannot believe how many of you there are, and in the overflow classroom. So anyways, welcome. Our first announcement is something fun. We have the College of Engineering barbecue, so free food. I know everyone loves that. It'll be Thursday from 11 to 1:30. So please come join us for some free food and get to know some other engineers. Okay. Good question. I asked the same thing. We are guessing that it is in front of HREL, which is kind of in between by the quad, and then you've got Palmer Engineering and SEM. But we are going to verify that and get it up on Wednesday, so you'll have 12 hours notice. Okay? So just plan on free food Thursday, and we'll get you the location. Anybody else? Questions before we get started? No? Okay. All right, so did you guys set up your clickers? Yep. Good. Channel 65, if you were in here in the big classroom. Channel 51, if you were in the overflow classroom. Okay. So points are counting these days. I know Dr. Lacombe said to check your grades to make sure your clicker's working. If you went to check your grade and you saw you don't have a grade, don't have a coronary yet. You're too young for that anyways. But we are working on that issue, and they should be posted tonight. So please check maybe late tonight or tomorrow morning or something like that, and make sure that your clicker is working, because it does add up to points throughout the semester. All right, so 10-day plan. You guys have reading quizzes all the time. They're due every Wednesday at 11:59 p.m. Please don't log in at 11:57. If it times out while you're taking it, then you get a 0. So make sure that you get in there early in case you have any problems or something like that. But please get used to taking those. They'll be due on Wednesdays. Your team charter, the due date got pushed back to this Friday. And you'll, yay! All right, who doesn't like to procrastinate a little bit? Friday by 6 o'clock in the EDL, so make sure you guys drop those off, get them to a TA or to Dr. Lacombe or I. And please keep a copy. It goes in your team journal, which I'm sure is near and dear to your hearts. You guys are going to keep track of all semester. Skills lab assignments are due at 11:59 on the night before your next skills lab. So if it is the night before you go to lab, stay home and do your homework. Make sure you get done. Don't wait till then. Yeah? He asked if it shows that, or if he has class on Thursday and it shows it's not due till Sunday, is that okay? No. A resounding no. Thank you for that question. That is a great one. Your homework is due the night for your skills lab. We attempted to set it up so we'd have variable due dates, but it turned to be a major headache. So it may say Sunday, but the TAs, before they grade your homework, are going to go through and look at what time it was turned in. So make sure that it's in by 11:59 the night before. Okay. You know your TAs. They have nothing better to do at midnight, so they're going to log in and check. Joking. I say a lot of bad jokes. I'm sorry in advance. All right. Anybody else? Questions yet? No? Okay. Also this week, online lifting fan learning module and quiz is due Monday. Okay? Monday by 11:59 p.m. That one will take you a little time, so please log in early. It will be available after class today. I'm going to go over lifting fans today and all the calculations and how to choose one, and then the online module will reiterate the information that I give you. Okay? So lots of due dates. All right, a simple request. You guys have seen this a lot by now. Please use the word ENGR100 in the subject line of your emails. We all get tons of emails. You guys get tons of emails. You guys are a priority. If you put ENGR100, we will make you our priority. So I like to get back to you guys quickly. If you don't put that in the subject line, though, it can get lost. Okay. All right, so last week, Dr. Lacombe was lecturing and ran out of time. So I'm going to pick up where he left off and then start into lifting fans. So he was giving you a basic summary of all the different parts of the Hovercraft and what you need to in this class and what goes into them and how they work. I'm going to continue with that. I'm going to gloss over these next few slides a little bit because there will be lectures pertaining to each topic, and they're coming at you in the next week or two. Okay? So next up, I think he was talking about decks. You want them lightweight and sturdy, right? and he talked about plenum chambers. That's what traps the air under your hovercraft. And then he got to batteries. You need batteries to run your lift fans, and you're going to need batteries to run your NXT. So you need something that is going to be cheap, right? You guys are college students. No one wants to spend extra money. So you need an economic battery, and you need something powerful. Mainly, you need something that's going to last through testing, checkpoints, final competition, showing your friends in the dorm your cool hovercraft. Okay? If you come to a checkpoint and your batteries last for 5 minutes, and you're testing, and then you run out of batteries, and you have to go plug it in for 3 hours or so, it's going to be really difficult to get done. So you want to make sure that you choose batteries that are cheap and powerful. Okay? And we will have an entire discussion about batteries, I believe, on Wednesday, so you guys will get a better idea of what you need. So some common ones are 7.4 volt car, RC car rechargeable, and then also AA nickel metal hydrides, and you'll get them in a 10-pack. Okay, so those are the commons, but we like you guys to be creative. You guys can come up with other ideas, and we can discuss them as the semester goes on. Questions about batteries? Anyone? No? Okay. All right. Fuel cells. We get to play with fuel cells in here. That's pretty cool, right? You guys are going to get a dual cell in series. The input is going to be hydrogen and air. So you get hydrogen, a balloon, and you're going to pump it through your fuel cell. And output, what you get out is electricity and water. So it's pretty neat, right? Has anyone played with fuel cells yet? A couple of you guys? Any alternative energy people in here? A couple of you guys? Good. Okay. So what we're going to use these for is for propulsion. They weigh about 6 ounces, and they only produce, these ones that we have, about 2 watts at less than 3 volts. So not a whole lot of power is coming out of these. There's not enough to really run a fan. But you guys need to come up with a creative way to use the fuel cells to get your hovercraft to the end of the course and coming back. You might want to run a small motor or something like that. It can move a small mass. Okay? You got to be thinking. Start thinking creatively. Read your textbook. Do some brainstorming. How are you going to control this hovercraft? It's got to get down and come back without hitting the wall. Okay? So fuel cells will be used for propulsion. All right, the control unit, Lego NXT. Who's played with Lego NXTs? Quite a few of you guys. Good. Lots of experts. All right, so the NXT receives inputs and it sends outputs. You guys, for inputs, are going to be using sensors. You guys have access to distance sensors and light sensors. Okay? And then your outputs are your motors, and you're going to send signals to your fans to turn them on and off. Okay? So you guys can see, I'll go over this side here. This is a picture of the NXT if you're not familiar with them. Okay? Down here, you guys can look at this later online for people who can't see. There's motors. Okay? Those are your outputs. Your inputs are sensors. And so down here, you'll have light sensors and distance sensors. So that is what you're going to use to control your hovercraft. Some of you might say, I've never played with an NXT. What are you talking about? Don't worry. Okay? We're going to go over programming in lab. We're going to use LabVIEW to control these things. And we'll talk about in class and in lab. You guys will get the opportunity to program these a lot. So you'll be experts, hopefully, by the end of the semester. Questions yet? These are easy. Okay. All right. $300 budget. I believe this was a clicker question last time. If you missed it last time, don't miss it if it gets asked again. You guys have $300 between your team, whether you have 4 members or 5 members. Okay. So the budget is for the total, complete cost of your hovercraft. So that means if you were to choose non-rechargeable alkaline batteries, which we highly suggest that you do not, but if you were going to choose them and they're not rechargeable and you use them for testing, you'll be stuck in that part of the design process for quite a while. And then you go from there and you come in and you use them for checkpoints, and we've got the final competition, but you want fresh batteries because you want to have the fastest hovercraft you can have. You start going through those. Batteries. Someone's running out to the student store to buy batteries, and every single battery goes in your budget. Even if your hovercraft only runs on 8 AA batteries, every single battery you buy goes into it. If you go with the decking material, say you try and use plywood, go against what we suggested maybe and say, I can use plywood, I can do it. And that's fine. And then at some point you decide, my hovercraft is really, really heavy. I need it to be lighter, I'm going to go with styrofoam. Guess what? The plywood and the styrofoam all go into that $300 budget. We don't want you guys to spend a whole lot of money. We're trying to save you money. But that being said, we need to make good design choices. So that's what engineering is about, right? We're going to do lots of calculations, design our hovercraft on paper. You guys are going to tell us what you plan to do, and we'll approve it and go from there. But please keep in mind, whatever you purchase, it all goes into your $300. Questions yet? Yeah. If you have materials that are free, you are very lucky. I say use them. Yeah, if you can find stuff around, please don't destroy a desk to make a hovercraft deck. Okay. But yes, if you have access, we can discuss. Anybody else? Questions? No? Okay. More bad jokes, right? All right. Do not buy anything yet. Please don't buy anything yet. Okay? We want to look at your designs. We don't want you to buy a bunch of things and then have to ship them back and waste money back and forth, and you order from someone who doesn't take returns and blah, blah, blah. So do not buy anything until we approve your design. You guys have a design concept paper due that eventually that you're going to tell us what you're going to do. You guys have all your calculations will be due. The TAs and Dr. Lacombe and I will look over those and approve them and then tell you to go buy. So please don't buy things yet. Wait. All right, so the main topic for the day is lifting fans. You might want to jot down a couple notes here. You can follow along with your calculators. A little bit of math today. First off, though, to tell you what I'm going to tell you for the day, you guys will get used to that for your presentations. We are going to talk about lifting fans and how to choose them. And we're going to look at some examples. But first off, we have to talk about what types of fans are there, okay? The design procedure and how we do that. And then we're going to do an example calculation to kind of finish up class today. So we'll go through all these things. It's a lot of information, just be warned. Okay? But you guys can go home tonight and you can do the lifting fan module. And there's also a video that shows you how to do this. And you can, you guys are doing fans in Skills Lab this week. So you'll get to see this many, many times. If I'm going too fast and you have a question, just raise your hand. If I don't directly see you, it's hard to see everyone all at once, yell or something, jump up and down. Okay, so hovercraft components. You guys have your lifting fans, your deck and plenum chamber, the control unit, batteries, and then the fuel cell and motor. Okay, so we are focusing on lifting fans from here forward. All right, we've got two things for you here. First off, has anyone made a hovercraft out of a balloon and a CD? A couple of you guys? Great. Okay, so this CD here is attached with a little water bottle top, and you blow up the balloon. Okay? As the balloon is releasing air, okay, it's forcing pressure underneath the CD, and the CD is floating, so it moves around on a frictionless surface. Okay? So your air, the balloon, is what is supplying your energy. It's forcing air down, and it creates pressure. Okay? Same thing goes here. I've got this large, huge military hovercraft. I know you guys talked about big hovercrafts last week a little bit, but you can see these guys are running out of the way. This is going to take a lot of power to get that off the ground. It's a pretty neat picture. So hovercrafts go on all scales. We've got the small little balloon one we can make, ours in class, up to the military hovercraft. The Kiwis hovercraft you guys saw, they got flying around in New Zealand last week. Did you guys watch that video? I think so. Yeah. All right. So question number one for your clicker. Remember, you got to create pressure under your hovercraft. What's that? Thank you. I'm pulling a Dr. Lacombe. All right. Hovercrafts are commonly used to float above water, concrete, sand, snow, and ice. Can a hovercraft hover on a surface made of mesh chicken wire? Yes or no? Remember, your hovercraft needs to create pressure. You got to force air down and create pressure. Oh, no. Oh. Well. Man. You guys lucked out. Let's see here. Oops. Bear with me. Oh, I don't know if you guys were quite saved. Let's see. Okay, you have a question? No, he's asking a question. He thinks he got his answer in. He was one of the lucky 27 in here. Good job. I think you should answer again. Yes, please. We'll try again. Sorry. We'll see how this works. All right, ready? On your marks, get set, go. What's going on? $377. 5, 4, 3, 2, 1. This makes me very happy. This means I'm doing my job. Okay. If you are, your hovercraft, if you just had a mesh surface underneath it, the air will go right through. And if the air goes right through, you have nothing to build pressure on. So the air needs to go down to a hard surface. You need to trap that air. And as the air is trapped, your plenum chamber is going to fill up and create pressure, and you will get lift. Okay? Questions? All right, good job, good job. Sorry about the confusion. Okay. Moving forward. So your lifting fans are going to direct your airflow right underneath your craft. Your fans could be facing directly down if you want them to, or they could be facing a different direction, but you're going to need ducting that forces the air down. Okay? So the idea is that the air is going underneath your craft. You want it to fill up that plenum chamber. Remember, the plenum chamber is what's trapping your air underneath your hovercraft. So as the air is pushing down onto the ground or the track, that is going to slowly force your hovercraft off the ground. Okay? So you need that plenum chamber, hard skirt, to trap the air. So not enough lift is going to cause your hovercraft to not get off the ground, in which case, that's enough. Let's try and get off the ground. All right? So if you get too much off the ground, your hovercraft can tip over like this guy over here, right? He's about ready to go backwards. So be careful. With your guys' hovercrafts in here, you kind of want to find that sweet spot, because if they're too high, they're going to be really hard to control. You're not going to have any friction whatsoever. It's going to be very difficult to get, well, it'll be easy to go down. It'll be hard to go down in a straight line and make it back. So you want to find that sweet spot. And we'll talk about an ideal height today. All right, so there's two types of fans. The first is similar to the ones you guys probably use in your dorms that don't have air conditioning. It's just an axial fan. And what it means is that the air goes in on one axis and comes out along that same axis. So axial fans, air goes in on one axis, comes out on one axis. And we'll look at some characteristic curves in a minute so you can see the difference. The second fan, which you may or may not have seen before, is a centrifugal fan. And what happens with the centrifugal fan is our air goes in on one axis and it comes out perpendicular. Okay? So you guys can see on the arrows on the PowerPoint here, we've got in one axis, out the other. And the fans can be used for fundamentally different things, and I'm going to go over each one of them now. You guys can decide which ones you guys want to use. All right, so first off, we've got our axial fans. Those are the ones that are presumably in your dorm rooms. Okay? Air in on one axis, out the same. The advantages to it is you get a high volumetric flow rate. Now, what the heck does that mean? That means that it's pulling a lot of air. A lot of air can go through there. You can get air through the entire part that's showing here. So it can pull a lot of air. Okay? It's simple shape. Building with squares is pretty straightforward. That's kind of nice. Okay? But the disadvantage to the axial fans is that they have a lower pressure differential. So remember, when we're talking about lifting, we're talking about creating pressure. You want to force air down to create pressure so you can get lift. Okay? These fans draw a lot of air, but they don't give out a lot of pressure. You guys have hopefully you guys have seen computer fans. That's kind of what we're talking about here. If you have a computer fan running, you don't get a huge breeze if you put your hand in front of it. right? Not a whole lot of pressure coming out of there, but a lot of air comes through. On the other side of things is the centrifugal fans. And this, again, you get air along one axis and out perpendicular. The nice thing about centrifugal fans is that you get a high pressure differential. So there's a lot of pressure coming out of these fans. The disadvantages is it's not pulling as much air as an axial fan, and it's more complex. Kind of looks like a funny little conch seashell. So it's a little harder to build with, but I have faith you guys can do it. Okay? But that's the difference. So a centrifugal fan, you get air in one axis, out the other, and you get lots of pressure. Yes, in the back. By comparison, which one ends up being hotter? I would assume that the centrifugal is going to run a little hotter because it typically draws more amps. Okay? Yes?
Why do we care?
Why does it matter how much air the fan is bringing in versus pushing out? Right, but why the high volumetric flow rate? Okay, good question. If you were going to say use, well, you guys aren't because you guys are using fuel cells, but if you guys were going to use these fans for, say, propulsion or something, you might want to affect more air around you because it gives you more steering control, something like that. Exactly. If you were using back fans, if you had fans on the back of your hovercraft, they're going to control more. For you guys, the focus is to get off the ground and get high pressure. Okay? But I want to give you guys, we want to tell you guys about the different fans available so you guys can make design decisions, right? That's part of the process, is seeking information. Anybody else? Good questions. Thanks for those. Okay. Next up, here's some curves to take a look at. And you guys got to learn how to read fan curves, fair warning. Okay? There might be a question coming about them. These two fans are very, very similar. Okay? They have similar RPMs. That means that their rotors are rotating at the same rate. They're both 12 volts. 3 watts versus 3.5 watts. They weigh about the same. Okay? Essentially, they're pretty much the same, but one's axial and one's centrifugal. There is a big difference here. You'll notice in our axial fan, if you guys can see this far, the pressure ranges from 0 to 70, okay, versus on our centrifugal, we're from 0 to 200 on this graph. My flow rate, okay, that's how fast the air is coming through there, that volumetric flow rate. On the axial, I've got 0 to 2 down here, centrifugal 0 to 0.6. Okay. Got one more graph I'm going to show you on the same graph. You'll see the curves and they look a lot different. But what's to keep in mind is when we look at lifting fans, we need to know how much pressure am I getting from that lifting fan? So if I said that I needed, let's go with something on both. Let's say I needed 40 pascals. And we'll look at this 12-volt fan. 12-volt fan is in red. You'll find these fan curves when you look them up later. They have a bunch of different fans on the same or on the same graph. So please make sure you're looking at the fan that you want to purchase. But anyway, so if I have a pressure of 40, I'm going to come across until I see the line that represents the fan I want. And our 12 volt is in red. So if I go across that red and drop down, you can see that at 40 pascals, I can only get about 0.2 meters cubed per minute. So just for a comparison for you guys, if I come over here and I look at my pressure, okay, 40, going across to my red line here, that's my 12 volt fan, and drop down, I'm getting about 0.3 meters cubed. Okay, so 0.3 versus, what did I say, 0.1 or so? 0.2? Okay. Makes a difference. Oh, actually, sorry, did I go? No, we're good, we're good. All right, so let's look at them on the same graph. Maybe this will help if you didn't buy the difference yet. Okay? The red curve is the centrifugal. We can tell because it's got that high pressure. Okay? The blue curve is the axial. In lower pressure, but more CFM. You could end up anywhere along this curve with your hovercraft. It depends on what pressure you're operating at. Okay? So if you needed a pressure of 60, this fan just won't work for you at all. That axial fan won't. But you could use the centrifugal fan. And I'll show you another example as we do calculations. But keep in mind, so you look for your pressure first, okay? Follow the x-axis along to that curve and drop down to find what your flow rate is going to be. Who has questions? Okay, moving forward. What? Question? Did I forget someone? Yes. What if you had more than one fan? Would it affect the numbers? If you have more than one fan, you can add up the flow rate, which is a very good question, because you very likely might have more than one fan. You can add up the flow rate. You cannot affect the pressure, though. So if you have two fans at 0.2 pascals, that does not equal 0.4 pascals. The pressure remains the same, but the flow rate will double or triple however many fans you have. Anybody else? Yeah. For lift, he said, do you really want pressure or flow rate? Or you really want pressure. You really want pressure. That's what matters when you're talking about lift fans. If you can't meet the pressure, you're not buying that fan. Yeah. The flow rate is, we're going to go over some math equations. You'll see at the end, you need a certain flow rate also to get off the ground, but the pressure is the most important part. So the flow rate second. So I guess my point in all this and reiterating it, and we'll get to flow rate, is that you need a required pressure, and then once you have that, then you make sure that you have the CFM you need. So you need both. I just don't want people seeing a flow rate. If they need 100, I don't want them seeing 100 and not matching the pressure. Question over here? Same thing? Okay. I think as we do the math, it'll help make sense. Yeah. Can you use what? Can you use both fans for lift? Yes. You can use either fan you want. What we'll do is I'm going to show you guys the lifting fan calculations today, which will be the start of your hovercraft design. We'll go through those, and you guys can select fans. And as long as you can prove to us that you guys have the pressure and the flow rate you need, then you can use them. Anybody else? Yeah. Sorry. CFM stands for cubic feet per minute. So you are going to find a flow rate, which is denoted by Q. Again, we'll get there. And I'm sorry, sometimes I say CFM in short, but it's cubic feet per minute, or like on this graph, you'll see meters cubed per minute. A lot of the fans you're going to be buying will be in cubic feet per minute. Excuse me for that. If you have any kayakers or rafters around, you guys might know CFS, cubic feet per second. Yeah, the rivers are done in CFS. All right. Anybody else? Okay. Okay, so the procedure. Chapters 3 and 10 will be very helpful to you. Please read them. All right, and you also have the online module on lifting fans, keep in mind. So I'm going to give you guys the steps for designing your hovercraft's lift or choosing fans. Things in red are things that you choose. Things that say calculate are things that are just governed by math and physics. You can't change. But things in red are the things you choose, and that's the beginning of the design process. You get to make these choices, and remember the design is iterative. So these choices you make, everyone in here is going to have, we'll create that everyone in here has different hovercrafts, right? Because you can all choose different things. So the first thing you want to do is you want to estimate the weight of your hovercraft. And we'll use Excel to do that. And I'm going to show you guys an example. I'm going to list out the steps, and then we'll go through step by step with an example. But first thing you need to do is estimate the weight. So this means looking at how much the NXT weighs and the fuel cell, and looking at how many fans you think you need and batteries, and coming up with an estimate. It's not going to be exact. I get that. It's okay. But you need a good estimate. So first thing is estimate the weight. Second, choose the desired gap size. Okay. The gap size is going to be how high off the ground your hovercraft goes. So it's the gap between your plenum chamber and the ground. We would suggest between 3 and 5 millimeters. That is typical. When we do our example, we'll do 5 millimeters, so we'll err on the side that gives us a little factor of safety, so we can make something heavier if we need to. But second one is choose the gap size. So again, choose is in red. That means that's something that you design. You guys think about what you want to do. All right, so we got a weight, we got a gap size. Then we need to choose the shape and the size of the deck. Any shape you want, square, rectangle, triangle, trapezoid. You can make it a giant star. I don't know. Anything you want. A soccer ball. Okay. And then once you choose a shape, you need to estimate the length, because you're going to have to calculate the area and the perimeter. So choose any shape you want, but keep in mind that you need to be able to calculate the perimeter and the area of that shape, as well as construct it and balance it. So, our things in red here. Again, we've got our weight, the gap size, the shape, and the size. So those 4 things you can iterate later if you need to make changes. These are your choices. From now on, we're getting to more of the calculation side of things. You have to follow. So we'll calculate the perimeter and calculate the deck area. Okay, so start thinking about doing some brainstorming, doing some searching, reading your book, and finding out what shape and size is going to work best for you and your group. All right, so after we have our area and our perimeter, we need the pressure required to generate lift. Right, we've been talking a lot about pressure with these fans, and now we need to figure out what is that pressure. And after we get our pressure, we need to calculate the gap area. We'll talk more. The gap area is the area between, it's like the perimeter times your gap height. So it's a little bit of area between the hovercraft and the ground. Right, from there, 2 things left. We're going to calculate the exit velocity, or sometimes you'll hear me call it the leakage velocity, depending on the day. The leakage velocity is how fast air is leaking out the bottom of your hovercraft. And again, I'm going to go through each one of these steps, and I'll explain a little more about each step here as we go. I just want you guys to have this ready to go for it. All right, last but not least, we calculate the required flow rate of the lift fan. So we've got our pressure, and then we need to find out what is that flow rate we need. So Q or CFM or meters cubed per minute. And then we've done all our calculations. Yay, math time is over. We need to find the appropriate fan. Sometimes that's not possible. You may have been that group that waited till the last day to do your calculations and pick your fans, and all the other groups bought up all of DigiKey's other 300 fans. And so you might have to keep looking. And at that point, you can start over or iterate down there in blue. Iterate means you're going to go back to the things in red and make changes. What happens if I make my hovercraft a little bit lighter? What happens if I lower the gap size or make my deck bigger or smaller? All those sort of things. Okay? That's the iteration process, the fun part. And you guys are going to be designing an Excel spreadsheet that does a lot of this for you, so that'll be nice. It'll make it easy. You can plug in a number, and Excel says, magic, here you go. Tells you what you need to have. Are you guys ready for an example? Yeah, right, exciting. Okay. Step 1, estimate the weight. In Excel, you guys will have a chart. You'll see up here I've got my main components, starting with the lift fan. Okay. I think I need 2 of those. They're going to weigh about 0.6 pounds each. They get 1.2. You guys know how to put in equations in Excel now after Skills Lab this week, so this should be easy. You have your fuel cell and connectors and motor, NXT, some batteries, your deck, sensors, and relays. I have estimated these weights. They are approximate. So my approximate total weight I've come to is 3.03 pounds. This can change, but we needed to come up with an estimate, so here's our estimate. Yes? Good question. Do your units need to be in the US standard or metric? Either way, you will see on the rubrics, I can't remember exactly what they're in, but we'll tell you what we would desire. I do love metric, but a lot of things in this country are still US standard. So we go back and forth in engineering school. You'll see. All right, anybody else? Okay. Moving forward. Next up, choose the desired gap size. Okay. So 0.2 inches or 5 millimeters is the maximum. Okay, so we're going to use that for now because this gives us, again, a little bit of error room. If all of a sudden our weight estimate goes up, it's not that big of a deal. So we're going to use 5 millimeters for this, just for this example. The air cushion underneath the hovercraft is called the plenum chamber, and that is formed underneath the craft. The gap that I'm talking about is between the plenum chamber and the ground. So it's barely perceptible, but it's there, and it's going to be 5 millimeters in our case. If your gap size gets to be too small, if you calculate it and then you start adding a bunch of art materials and stuff to make your hovercraft look really pretty, sometimes it can get stuck on small bumps, tapes, ridges. Another team could like throw out a pebble or something. Hopefully they don't, but it can get stuck. Okay? It can also drag on the ground. That's kind of a problem. If you don't get off the ground, that's really a problem. If your gap size is too big, you're not going to have barely any friction, and no friction means that it's going to be really difficult to control. So we want to find kind of the sweet spot in between here. All right, so next step. So we have a gap height, and we have, what was our first one? Our weight. So now we need to choose the deck shape. Again, whatever shape you want, just beware that you have to calculate the area, the perimeter, and you need to be able to balance it. Okay? Common shapes are squares, rectangulars, circles, a bullet shape, or a big oval, things like that. You guys choose. That's something you guys can research as a group. So we're going to assume a square for this example. It's easy calculations. Okay? First thing I'm going to do is get the perimeter. The perimeter, we just add up the length of all the sides. And then we are going to get our deck area, length times width. Okay? And we end up with, what's it, 576 inches squared. So the start of the math is calculate the perimeter and the area. Next step is ready. Am I going too fast? No? Yes? No? No one's yelling at me, so I'll take that as a no. Okay. Calculate the required pressure. You'll see it as P REQ. Okay? P required, pressure required. Pressure required is going to be force over area. Okay? In this case, your weight is your force in pounds. Your area is in square inches. Okay? So your pressure required is going to be, we're going to say 4 pounds, okay? Because I don't want to rely on my weight estimate of 3. I want to give myself a little bit of factor of safety. So I'm going to go with 4 pounds divided by, was that 576 or 524? I can't remember now. Square inches. So we've got pounds per square inches. So if I divide my weight by my area, I end up with 0.0069 PSI. And a PSI is a pounds per square inch. It's just a measurement of pressure. So again, pressure is going to be the weight over the area of your hovercraft deck. Okay, so 2 numbers you already have, you divide them, and you end up with your answer, your pressure required in PSI or pounds per square inch. So next up, people say, well, what the heck is 0.192 inches of water? Inches of water is another measurement of pressure. It's an old school measurement you don't see very often. Has anyone heard of a manometer? A couple of you guys? Okay. So a manometer is like a U-shaped thing. It's got liquid in it. And basically you can measure pressure by applying pressure, and then the liquid goes up in inches, and you count those inches. There is an entire thing to read on manometers in your book. And in the lifting fan module, I encourage you guys to get that done this week before it's due. But you guys can get more information there. What you guys probably really care about is that 1 PSI is 27.7 inches of water. Okay. So we can take our PSIs and we can multiply it by 27.7. If you don't remember that number, Google has it on hand for you. You can multiply those numbers, and you end up at 0.192 inches of water. What's that? 27.7, yes. Well, close there. It's like 27.68 or something. But 27.7. 1 PSI is 27.7 inches of water. Right. So, I hesitate with this inches of water here because I put it up here because the fan graphs that you will look at, those data curves we were looking at before, they're either in pascals or inches of water. but they're not in PSI. So we convert this number to inches of water and then set it aside. The PSI number you have, 0.0069, is what we will use for calculations. Don't get caught in the trap of taking your inches of water and using it again. Remember, in all your engineering classes, your math classes, be sure to write in your units and carry them as you go, because then you can check for errors that way. Okay. Are we ready for the next step? Because I'm running out of time, I better get going. Okay, calculate the gap area. So the gap area is just the perimeter of your deck. You guys already have that number. And you multiply it by the height of the gap. We use 0.2 inches. So perimeter times the height of the gap. And it gets you this area where the air can leak out. So it's a little tiny area all the way around your hovercraft, and it's where the air can leak out of your hovercraft. And that is our gap area. Okay? So perimeter times gap height, easy multiplication, you got your gap area. Ready to rock. Remember, this is all online for you too. So if I get going too fast, I'll try not to, but you can always review. How what? Yeah, I converted. Sorry, I went from 5 millimeters to 0.2 inches. So this example is all going to be in the US system. Just keep it consistent, obviously. Okay, moving forward. Step 6, the exit velocity. This is equation 3.13 in your textbook. It's a simplified version. It comes from Bernoulli's equation, which you can read about and see the derivation. I'm not going to go over the derivation in class, though, because you can read about it. So basically, leakage velocity, that's what this V sub L is equal to the square root of 2 times the gravitational constant times the pressure required divided by gamma. Gamma is the Greek symbol. It's the specific weight of air at atmospheric pressure. Okay. G, in this case, gravity is going to be 386 inches per second squared. I know people say, no, G is 32.2 or 9.8, but remember your units. We're in inches per second squared. Normally we talk about feet or meters. Okay. So I have simplified this leakage velocity equation for you, and I took the square root of 2 times G divided by gamma and came up with 4.182 times 10 to the third, and you can multiply that by the square root of your pressure required. So a little bit of algebra. Okay. But the main thing you guys need is 4,182 times the square root of my pressure required is going to be the leakage velocity. And the leakage velocity is how fast is that air coming out from underneath your hovercraft. You'll be able to feel it when you get it built and going. But it's right here with these arrows. Okay? Your leakage velocity is how fast is that air coming out. Again, 4,182 times the square root of pressure required. The main thing to remember is that pressure required is in PSI. In this case, carry your units when you do the math. If you put in those inches of water, you will get a really wrong answer. So make sure you stay in PSI. This pressure required is in PSI is pounds per square inch. So before we converted the pounds per square inch into inches of water, and you only use that number for graphs. I just want to make sure you guys know that. This pressure required is in pounds per square inch. Okay. I know it's confusing, pounds per square inch, inches of water, but pounds per square inch. Right here? So your gravity is an acceleration, so it's in inches over, or distance over time squared is always going to be your acceleration. Here, inches per second is a velocity. If you get confused about those, just think miles per hour. That's something very familiar to us, velocity, speed, distance over time. Good? Yeah. Okay. Bear with me, you guys. You got 6 minutes. All right. Now we need the flow rate. Final math bit here, 1 multiplication. Okay? The flow rate is denoted as Q in pretty much all your engineering classes. Sometimes variables mean different things. Usually Q is flow rate. Q is your leakage velocity multiplied by the area of the gap. So 2 numbers you have. We just calculated the leakage velocity, and we did the area of the gap 2 slides ago. Multiply those 2 numbers together, and you are going to get your flow rate. That flow rate, with the units we've been using, will come out in inch cubed per second. Those fan data curves, though, they're in inches of water and they're in CFM, or cubic feet per minute. So this last step here I did, and I didn't show you guys the math, you need to convert your inches cubed per second to feet cubed per minute. Okay? Inches cubed a second to feet cubed per minute, and that's the CFM, cubic feet per minute. So you can multiply by 60, divide by 12 cubed, you can get there. You guys can do that on your own. But make sure that you're in the units that the data curve has. So that was the final math step. Now we have to find a fan. Anyone need time? Yes. Okay, I'll wait. Go ahead. 232 is the flow rate that we are looking for. So we calculated that pressure required of 0.0069 psi, right? We care about that number, and we care about this number, 232 CFM. So the idea is we need to find a fan or multiple fans that equal 232 CFM. And the pressure. Pressure first, we check pressure first, and then we check CFM. Okay. Are we good? Okay. All right. So to pick a lift fan, yes? No worries. In PSI. Or sorry, when we look on fan curves, only when we look at curves, we look at it in inches of water. Okay? Okay. So go to digikey.com, QuickFlow, or some sort of computer parts place, and they'll have fans. If you go to DigiKey, it's super easy. They have zillions of them. You search fans. Go to DC fans. Okay? So we're using batteries here. You want in stock and 12 volt. Make sure you choose in stock. DigiKey will list stuff that they will have in a year from now, and that's not going to be very good for your grade come December. So make sure it's in stock. You can filter the flow rate by CFM, which is nice. You view page, and you get something like this. Okay. And remember, this is all in line. Okay. So make sure you have DC 12 volt fans. Are we good? You guys give me 1 minute, 1 minute, 1 minute, please. I think I have 2 minutes officially. Are you ready? Okay. You guys will get a page like this. Okay? These are your choices. You've got 0.2 inches of water, 0.268 inches of water, 0.313, 0.268, and you can see the different CFMs. The prices are over on the other end. You probably also care about those. Okay? We need to find something that meets the pressure that we need. Once we have that pressure, then we check CFM. Yes, they have all sorts of fans. All right, give me one more slide, one more slide. It's 48 after. Okay, you guys, there is a Q of 232 CFM. Your pressure required is 0.192. So what you guys need to do is look on here for 0.192. Okay, that was it. Pressure required, the weight over the area from the beginning. Find 0.192 on the graph. The line goes across to your fan curve. Once you get there, drop directly down, and that is a CFM that you're going to get. So you're getting about 95 CFM. You make sure you go to the pressure required first, follow it across, and drop down, and you get your CFM. Okay? So for this fan, if you need 95 CFM, and we need 232, we would need 3 of these, but we only estimated for 2. So that means that we'd have to add another one that changes our weight, and it changes how high our hovercraft hovers, and we're into this iteration process and reiteration. And last but not least, I have a clicker question before you go. Oh, what is the flow rate when pressure is 0.08 in inches of water? Okay, what is the flow rate? I will hit go right now. 30 seconds. Ah, sorry. There you go. 1, 2, 3, or 4. You can see it. You have 0 CFM, 25 CFM, 45, or 60. When you're done, you can take off, and we'll see you Wednesday.